On November 10th, a quiet alert stunned the astronomy community. A satellite report confirmed that 3I/Atlas had shed a significant portion of its structure after its latest brush with the Sun. Once it crossed perihelion, calculations showed that 3I/Atlas had lost nearly 13% of its total mass, an estimated 4 billion tons of material suddenly gone. According to basic physics, such a violent outgassing should have produced a spectacular tail, a blazing ribbon of dust and ice stretching millions of kilometers behind it. But the images sent back by China's Tianwen-1 orbiter told a very different story. Instead of a brilliant cometary tail, the probe captured only a faint, compact sphere of light, no debris, no extended trail, nothing that explains what happened to those 4 billion tons. This disappearance marks the 10th anomaly in a growing list of behaviors that defy every established model of cometary motion. When astronomers multiply the probabilities of these 10 irregularities occurring naturally, the odds fall to less than 1 in 10,000, perhaps even 1 in 100,000. So the question is no longer simple. Are we witnessing a natural phenomenon unlike anything ever recorded? Or does the pattern point towards something we do not yet have the language, the physics, or the framework to explain? The journey of 3I/Atlas is far from over. New observations are already underway. And after this, we will finally reveal the 10th anomaly, the one that breaks every known rule of comet behavior. 3I/Atlas only entered our awareness because a distant robotic explorer happened to look where no Earth-based telescope could see. While observatories focused on other targets, China's Tianwen-1 orbiter quietly received a new command.
Impact window.
Turn away
It's
from
much
Mars,
sooner than we
its
thought.
home of 4 years, and point its precision cameras toward an object 30 million kilometers beyond. That object was 3I/Atlas, traveling at 58 kilometers per second, or 129,000 miles per hour. Fast enough to circle Earth in under 20 minutes. Fast enough to break expectations before anyone could even react. Its core, only 5.6 to 6 kilometers wide, roughly the size of Manhattan, was darker than asphalt and colder than forged steel. Tracking something so small and so dim required absolute perfection. Tianwen-1 systems were built for planetary surfaces, bright, stable, predictable. Now they were asked to follow a racing ember streaking across the sky faster than the spacecraft's original targeting algorithms were ever designed to handle. For weeks, engineers recalibrated the orbiter. Every adjustment was a calculated risk, balancing precision against the possibility of losing the object forever. A tiny error, a fraction of a degree, and 3I/Atlas would slip back into the black, gone without a trace. Then the effort finally paid off. CNSA released a sequence of raw monochrome images, a faint sphere surrounded by a slowly expanding glow. The coma of Atlas stretched thousands of kilometers into space. The frames were sharper than Hubble, crisper than James Webb, and far clearer than anything ground-based telescopes could achieve through Earth's atmosphere. For the first time, humanity had captured a true portrait of an interstellar visitor in motion. 3I/Atlas was no longer a distant hypothesis traced through equations. It became a real object, with weight, light, and presence. But the images revealed more than success. They revealed contradiction. The halo around 3I/Atlas was unnervingly smooth, almost peaceful. No jagged jets. No chaotic vapor trails. No evidence of violent outgassing under intense solar heat. Where physics predicted turbulence and disorder, the camera found symmetry and calm, light shimmering evenly, as though held in place. Tianwen-1's achievement delivered not just a picture, but a silence. And in that silence, the mystery deepened. When 3I/Atlas passed its closest point to the Sun, something invisible but measurable happened. The object deviated from its predicted orbit, moving as though nudged by an unseen force. NASA's Jet Propulsion Laboratory confirmed a phenomenon known as non-gravitational acceleration, a faint but persistent push normally produced when gas escapes a comet fast enough to shift its trajectory. The measurements were precise. At 0.09 astronomical units from the Sun, the radial acceleration was 1.1 times 10 AU/day superscript 2, pushing the object outward. Along its orbital path, the transverse component measured 3.7 times 10 AU/day superscript 2. Momentum calculations pointed to a single conclusion. 3I/Atlas had lost nearly 13% of its total mass. Roughly 4 billion tons of rock, gas, and volatile ice had vanished within days. Physics demands that such a loss blaze across the sky, a brilliant cometary tail, an expanding plume, a storm of dust. But Tianwen-1, ESA's Mars Express, and Earth's observatories all saw the same thing. Nothing. No tail. No fan of dust. No turbulence. Acceleration was real, yet the evidence of outgassing was gone. A reaction without residue. A propulsion with no exhaust. For astronomers, this became the first verified contradiction, motion that left no trace. And from that contradiction, 3I/Atlas whispered the beginning of a deeper story. 3I/Atlas entered the solar system as if it already knew the map. Its path wasn't random, wasn't chaotic, wasn't the scattered trajectory expected of an interstellar wanderer. Instead, it approached almost perfectly aligned with the ecliptic plane, the thin, invisible sheet where all our planets orbit the Sun. Its inclination? Barely 5 degrees. A value so small it echoed the precision of planetary formation itself. That was the first geometric alarm. Comets aligned with the ecliptic because they were born in it, forged from the same disk that formed Earth, Mars, and Jupiter. But 3I/Atlas came from elsewhere, thrown out from another star system entirely. Its orbit should have been tilted sharply, vertical, or wildly angled. Yet Atlas arrived nearly flat, tracing the same plane as the planets, but moving in the opposite direction. Retrograde motion inside a coplanar orbit is extremely rare. It's a mathematical contradiction, like a leaf sliding upstream on a river's surface without dipping above or below the flow. The probability of an interstellar object entering within 5 degrees of the ecliptic is about 0.2%, 1 in 500. Astronomers rechecked everything. Maybe early data was skewed. But independent analyses from JPL, ESA, and CNSA all confirmed the same orbit, the same alignment, the same retrograde flow. 3I/Atlas wasn't following a random path. It was tracing geometry with unsettling precision. Some speculated it might belong to an unseen stream of interstellar debris shaped by the Milky Way's gravitational midplane, but no such structure has ever been detected. Others wondered whether the alignment itself carried intent, optimized to intersect planetary space for reasons unknown. Emotionally, the discovery shook the scientific community. The ecliptic is our cosmic foundation, the architecture of our world. For an alien object to enter cleanly along that plane, inverted, precise, felt like a foreign signature written in familiar handwriting. It was the moment when standard celestial mechanics began to fail. And from that silent alignment, the mystery of 3I/Atlas opened its next chapter of defiance. But the anomalies did not stop there. Between July and August 2025, telescopes worldwide recorded an impossibility. A jet of material erupting toward the Sun, not away from it. Every rule of thermodynamics and solar dynamics forbids this. Sunlight pushes dust outward. Solar wind drives tails away from the Sun. Every rule of thermodynamics and solar dynamics forbids this. Sunlight pushes dust outward. Solar wind drives tails away from the Sun. This principle is so absolute that astronomers use tail direction to identify a comet's position without even seeing the nucleus. Yet 3I/Atlas broke that compass. Its jet advanced into the Sun's face. Some suggested an optical illusion, a known antitail effect caused by angle distortions when Earth crosses the comet's orbital plane. But observatories in Chile, Japan, and Italy all recorded the same orientation at the same moment. Geometry ruled out coincidence. Physics ruled out randomness. 3I/Atlas was expelling material into the solar wind, an act that should be impossible. For a natural body to do this, it would require an extreme rotational configuration that should have ripped the nucleus apart. Even then, The expelled gas should have been blown backward instantly. And yet, it wasn't. Centrifugal forces alone should have torn the nucleus apart. Even in the most extreme scenario, any gas expelled toward the sun would be forced backward almost instantly by solar wind, bending the stream into alignment within seconds. But the jet from 3I/Atlas did not bend. It held its vector perfectly, steady, unwavering, for nearly 48 hours, a sustained defiance of every force acting upon it. Some argued that perhaps a magnetic field had redirected the flow, but the interplanetary field at $1 is far too weak for that kind of precision. Others suggested an asymmetric cavity on the surface, an oddly shaped vent that focused gas into a narrow stream. Yet even that would not explain its directional persistence. The jet behaved less like vapor released from a fracture, and more like thrust from a controlled nozzle. Emotionally, the data unsettled even the most disciplined researchers. The sight of 3I/Atlas pushing directly against the sun, advancing into the stellar wind as if challenging it, carried a mythic undertone. It felt less like meteorology and more like defiance, an object testing the dominance of the star that commands everything else. That sense of rebellion wasn't poetry. It was physics refusing obedience. The anomaly was catalogued clinically as jet emission oriented towards solar vector. But beneath that sterile phrase lingered an unspoken conclusion. A force was acting with intent-like precision, contradicting everything we know about passive cometary outgassing. 3I/Atlas wasn't simply reacting to sunlight. It was maneuvering through it. For as long as comets have been observed, their tails have always fled from the sun, shadows retreating from fire. But 3I/Atlas turned to face the light, and moved against it. 3I/Atlas was immense, fast, and statistically impossible. Its nucleus measured roughly 5.6 kilometers, an icy metallic city drifting between the stars. That alone made it extraordinary. But its speed transformed it into an astrophysical paradox. At 58 kilometers per second, or 129,000 miles per hour, Atlas was traveling faster than any object of its size ever recorded. Size and speed are not supposed to coexist in nature. Small fragments can be flung into interstellar space by gravitational slingshots. But a kilometer-scale mass requires unimaginable energy to reach escape velocity. 3I/Atlas broke that rule. It wasn't just massive. It was too fast, moving at a velocity that didn't belong to any known natural class. For comparison, Oumuamua was a small shard about 100 meters long. 2I/Borisov was a typical comet, only a few hundred meters wide. But 3I/Atlas dwarfed them. Over 1,000,000 times more massive than Oumuamua, and 1,000 times heavier than Borisov. Statistically, such an object should be among the rarest in the galaxy. Yet the third interstellar visitor ever found was also the largest and fastest. Models of galactic dynamics do not allow this combination easily. High-velocity objects tend to be small fragments from catastrophic events. Large bodies tend to remain gravitationally bound to their systems. To accelerate something as massive as 3I/Atlas would require a close pass by a neutron star, a collision near a black hole, or an engineered act of propulsion. None of these scenarios sit comfortably within known probability. Researchers attempted to reconcile the numbers. Maybe solar gravity had exaggerated the measurements. No. Atlas's speed before entering the heliosphere already exceeded interstellar escape velocity. Could it belong to a hyperbolic stream, debris shaped by galactic tides? Possibly. But no other object shares its trajectory. It was singular. Alone. Defying distribution models by orders of magnitude. Emotionally, astronomers described it as a statistical rebellion. Every rule said it should not exist, yet it crossed the solar system like a projectile carved from improbability. Was 3I/Atlas a cosmic accident of impossible odds? Or a traveler launched with intent? The anomaly summary was cold but haunting. Detected object exhibits extreme mass, velocity coupling inconsistent with stochastic ejection profiles. Translated into human terms, it was too big, too fast, too perfect a bullet. A natural object can break one rule, rarely two. 3I/Atlas shattered both, then continued forward as though reminding us that even in a universe ruled by laws, exceptions can carve their own path. Underscore 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 3I/Atlas did not simply enter the solar system. It arrived. Every segment of its trajectory seemed synchronized with our observational windows, as if following an invisible choreography. When Atlas crossed Mars's orbit, European spacecraft were aligned. When it passed Venus, active probes were watching. When it grazed Jupiter's outskirts, it remained detectable yet untouched. Each encounter was geometrically ideal. Then came the moment that changed everything. At perihelion, its closest approach to the Sun, Atlas should have been at its brightest. Yet, exactly at that moment, the Sun positioned itself directly between Atlas and Earth. From our planet, the object evaporated from view. Every telescope was blinded by daylight in the same direction Atlas passed. It was the most unobservable configuration possible. The odds of this alignment happening by chance were estimated near 0.005%, about 1 in 20,000. It felt as if the cosmos had dimmed the lights on purpose. From Earth, Atlas vanished. From Mars, Venus, and Jupiter's domains, it remained visible just long enough to be recorded. To any engineer, the trajectory resembled something optimized for reconnaissance, a path that skimmed major observation posts while avoiding the most monitored vantage point in the sky. Emotionally, the implication left a subtle unease. 3I/Atlas behaved as though it understood our geometry. Not literally, but unmistakably in its pattern. A strange unease began spreading through observatories worldwide. 3I/Atlas behaved as if it understood the layout of our instruments. Not literally, of course, but its trajectory moved with a precision that suggested it recognized the geometry of our observation network. In more than a century of tracking celestial bodies, no interstellar visitor had ever arrived with such theatrical timing. The official scientific report explained the event in cold, neutral language. Solar conjunction rendered the object unobservable from Earth at perihelion. But beneath that sentence lay something far more unsettling, the quiet belief that 3I/Atlas had executed a maneuver no random object could time so perfectly. This became the fourth anomaly, the one that made the idea of coincidence begin to sound like intention. And as Atlas exited the inner solar system with immaculate precision, a question echoed across every observatory log. Who or what engineered such a flawless disappearance? Underscore 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 underscore. But 3I/Atlas was not only a mystery of motion, it was a riddle of matter. When the first spectral readings arrived in mid-2025, astronomers expected the usual cometary signature: volatile ices, silicate dust, iron-heavy minerals. Instead, they found something impossible, a metallic signature dominated by nickel, far stronger than iron. No comet in recorded history had ever displayed such a composition. Ordinary comets follow a chemical pattern written during the solar system's birth. Iron dominates, nickel follows. 3I/Atlas broke that rule completely. Its spectral lines blazed with inverted chemistry, nickel overpowering iron by a margin no natural model could explain. Even more shocking was the presence of nickel cyanide compounds in amounts 10, 100, even 1,000 times greater than any comet ever measured. At first, ESA and JAXA suspected instrument contamination. Multiple recalibrations proved the readings were real. The discovery forced astrophysicists to question the origin of such material. A nickel-rich body might form near an older, hotter star, but even that theory collapsed under the purity of the signature. Nature simply doesn't create such extreme metallic ratios without leaving traces of iron or magnesium behind. Atlas's spectrum looked engineered, selective, deliberate, efficient. In laboratories on Earth, this same ratio appears in industrial nickel alloys, materials used for spacecraft hulls and thermal shielding, chosen for their resistance to heat, stress, and corrosion. The resemblance was unsettling. This didn't prove artificial construction, but the comparison was impossible to ignore. If one were to design a vessel capable of surviving millions of years of interstellar travel, a nickel-based shell would be an obvious choice. Emotionally, this discovery marked a dividing line. Up until this point, Atlas's anomalies could still be defended as statistical flukes. But this, the substance of the object, felt intentional. For the first time, nature's handwriting resembled human engineering. The official report stated it cautiously. Spectral data reveal anomalous nickel enrichment inconsistent with known cometary formation environments. Behind those careful words was a quiet shock shared across every data team. 3I/Atlas was not made of the same dust as the rest of the solar system. It was denser, harder, older, as if forged in an alien furnace or shaped by hands unseen. Then came the next fracture in our understanding of comet physics. 3I/Atlas was almost dry. Where a typical comet is a dirty snowball, this object was closer to a metallic stone with only a whisper of frost clinging to its surface. Spectral readings showed that only 4% of its total mass was water ice. By comparison, normal comets contain 70 to 80% water. This was no comet by conventional definition. It was something else entirely. Astronomers were stunned. Water ice is the engine of comet activity. It vaporizes, forms jets, and produces the glowing tails visible from Earth. If Atlas lacked water, then what powered the massive outgassing and non-gravitational acceleration observed near perihelion? Nothing in standard comet physics made sense anymore. Some theorized an origin near an unusually hot star, one where volatile materials were burned away early. Others proposed an asteroid-like object that accumulated thin layers of ices while drifting through interstellar clouds. But even those explanations collapsed when compared to the numbers. Atlas wasn't simply low in water. It acted as if it was built to function without it. Natural comets erode violently during solar encounters, cracking, fragmenting, losing structure. Atlas, despite losing billions of tons of material, remained remarkably cohesive. It resisted fragmentation. It held its shape. Its faint coma persisted without collapsing. An object with so little water should have been destroyed. Instead, it endured, almost like a designed structure, optimized for survival. Without water, its jets must have been powered by something else, perhaps nickel vapor, silicate gases, or a mechanism we do not yet understand. Whatever the source, it was stable, controlled, and sustained for weeks. This was not chaotic evaporation. This was regulated release. Even veteran astronomers admitted feeling unsettled. 3I/Atlas did not behave like a wandering relic of the early cosmos. It behaved like something built for a purpose. Sparkle's rephrased version, cinematic, meditative, mysterious. It no longer resembled a fragile wanderer shaped by ice and chance. 3I/Atlas looked more like a relic hardened by ages, a traveler sculpted for survival, stripped of every weakness. The thought was both awe-inspiring and quietly disturbing. We might be witnessing an interstellar body crafted not for beauty, but for endurance. The official reports put it delicately. Observed volatile fraction remains anomalously low. Primary composition inconsistent with standard cometary ice models. Yet between those careful lines, the implication grew louder. A comet with almost no water is a contradiction. A comet that still accelerates, still outgasses, still stays intact despite that dryness. That is a message written in the language of survival. 3I/Atlas may not have carried oceans, but it carried something far rarer. The ability to defy the very definition of a comet. And in that defiance, a question lingered. Was this the universe's most resilient wanderer? Or the oldest artifact ever to drift through our star's light? Sparkles the light that shouldn't have behaved that way. When sunlight finally touched the surface of Atlas, it reacted as though it were striking something unfamiliar, something alien. Ordinary comets scatter light in predictable patterns. Decades of observations have shown the same optical behavior, partial polarization, shaped by dust size, texture, and composition. Even interstellar visitors like Oumuamua and Borisov followed this rule. But 3I/Atlas shattered it. During its solar approach, telescopes recorded extreme negative polarization, a signature so rare that no known natural material could produce it. Instead of aligning light in the expected direction, Atlas twisted it backward, as if its surface were absorbing one orientation of light and inverting the other. Multiple observatories, from Italy, Japan, and even the Mars orbiters, confirmed the same effect. This was not noise. Not an instrument flaw. In simple terms, Atlas was bending light the wrong way. Its reflected rays implied a surface far smoother, denser, or more engineered than any dusty comet nucleus. Some scientists suggested metallic microstructures, fused nickel grains or ultra-fine crystalline films capable of optical inversion. Others proposed magnetically aligned plasma dust, acting like an artificial optical filter. But none of these theories matched any known natural formation. Negative polarization, at this strength, only appears in rare minerals or engineered materials, and only at specific angles. For Atlas to produce it, from millions of kilometers away, and at magnitudes beyond laboratory replication, was simply impossible. 3I/Atlas didn't just reflect light. It manipulated it. The data curves resembled results from laboratory laser experiments, not comet surveys. Emotionally, it stunned astronomers with a quiet awe, not the drama of an explosion, but the subtle defiance of an optical law. Every photon returning from Atlas seemed to whisper, "This surface is not what you think." Smooth, yet not polished. Reflective, yet not bright. Familiar, yet alien. The official summary tried to remain neutral. Observed polarization angles deviate significantly from all modeled scattering regimes. But behind those restrained words lay an uncomfortable truth. This interstellar traveler was rewriting material physics itself. Sparkles the trajectory that echoed a half-century mystery. Of all the strange alignments surrounding 3I/Atlas, one stood apart, an echo from nearly 50 years in the past. Its trajectory pointed back toward the same region of sky that produced the WOW signal, the most famous unresolved radio burst in SETI history. The match wasn't perfect, but at only 9 degrees apart, it was close enough to seize the attention of scientists around the world. The WOW signal, recorded on August 15, 1977, came from the Sagittarius region. Narrow band. Powerful. 72 seconds long. Never repeated. A single handwritten, "Wow," beside the printout became immortal. For half a century, no one knew where it came from. Then 3I/Atlas appeared, emerging from almost the same celestial corridor. Neither Oumuamua nor Borisov shared that direction. Out of tens of thousands of possible interstellar inbound angles, Atlas chose one that overlapped with the only unexplained narrow-band signal in human history. Statistically, the probability was calculated at less than 1%. Scientists were careful not to sensationalize it. Correlation is not proof. There is no established connection. But within SETI circles and interstellar research teams, the alignment became a quiet obsession. If the WOW signal had been artificial, a narrow band call drifting through space, then Atlas was arriving from its neighborhood. If the signal was natural noise, the coincidence was still extraordinary enough to deserve re-examination. Several teams rescanned the region during Atlas's approach. No second signal appeared. Yet the geometry remained uncanny. An interstellar visitor traveling from the one unresolved beacon in our radio past. Had the signal and the traveler shared an origin? Or had we, by sheer coincidence, looked twice into the same silent corridor of the galaxy? Emotionally, the realization unsettled astronomers. Not with fear, but with a strange symmetry, as though the universe were repeating a whisper we once heard but never understood. 3I/Atlas had already broken the laws of motion, composition, and light. Now it seemed to trace its lineage through the coordinates of mystery itself. The SETI network's final assessment arrived with an unusual quietness. Their report noted that the path of 3I/Atlas brushed within 9 degrees of the legendary origin point of the WOW signal. The odds that this was mere chance, 6%. No dramatic claims followed, only a single, almost whispered footnote. Further monitoring advised for future interstellar objects arriving from comparable coordinates. 3I/Atlas came and went without emitting a whisper. Yet its silence rekindled the memory of a transmission that echoed across decades, a message that crossed the void long before the object itself ever arrived, still drifting unanswered in the static between stars. Underscore 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 underscore. The night of October 29th, 2025 began like any other for astronomers watching the inner solar system. But within hours, observatories from Chile, Hawaii, and orbiting platforms all detected the same impossible surge. 3I/Atlas had brightened by a factor of 5. Not gradually. Not naturally. But in a single, flawless pulse, as if someone had thrown a switch. Ordinary comets behave differently. When sunlight heats their surface, they shed gas and dust, creating messy, chaotic, yellow-white halos. But 3I/Atlas refused to participate in that physics lesson. Its sudden glow shifted toward the cold blue of ionized plasma, sharp, metallic, unnatural. No dust. No vapor. No expanding debris. ESA's solar orbiter and China's Tianwen-1 confirmed it. The coma remained perfectly smooth and symmetrical, without losing mass. Brightening without shedding material, an impossibility under standard comet physics. Scientists scrambled for explanations. Instrument glitch? Sensor overload? Cosmic ray contamination? All eliminated within hours. The emission was real. Some suggested a plasma sheath excitation, solar wind energizing a conductive surface, briefly turning the object into a massive capacitor. Others proposed exotic piezoelectric reactions within a supercompressed crystalline core. Both sounded absurd. Both matched the data better than any natural comet model. Observers described the moment with an eerie calm. 3I/Atlas had already defied gravity, rotation, and composition. Now it challenged the meaning of light itself. For 70 continuous days, the object pulsed with unwavering luminosity, something no comet in human history has ever done without disintegrating. The official summary reduced the spectacle to 4 sterile words: unanticipated sustained photometric enhancement. But those who watched it live said something different. The comet didn't shine. It spoke. The glow felt like deep space lightning, controlled, deliberate, alive. And when it finally faded, all that remained was a spectral fingerprint, the moment the universe seemed to blink back at us. In celestial mechanics, one rule has always been inviolable. Mass loss must be visible. A comet shedding billions of tons of material should show it: bright tails, dust streams, gas clouds. But when 3I/Atlas passed perihelion and lost an estimated 13% of its total mass, about 4 billion tons, the sky remained disturbingly empty. No shimmering tail. No vapor plume. Nothing. A silent glow, sealed and spherical, surrounded a body that should have been ripping itself apart. Ground telescopes in Spain and Italy and orbital systems around Mars all confirmed the same absence. The direction where the tail should have been was void. Even long-exposure deep-field scans revealed no debris, no gas, no trace. It was as if the universe had swallowed the comet's scream. This anomaly struck at the center of astrophysical law. NASA's JPL data showed clear non-gravitational acceleration, a push that demanded expelled mass. But the expelled mass was nowhere. Where did 4 billion tons go? Some theorized the material escaped as superheated, ultrafine gases emitting outside the visible spectrum. Others imagined an electromagnetic barrier that redirected the outflow inward, an unseen containment field that trapped the comet's own exhaust. Both ideas sounded like science fiction. Yet both explained the reality better than the rules written in our textbooks. High above the Martian surface, tracing a long, looping path that carries it from pole to pole and far into the sun's shadow, Tianwen-1 orbiter performs its. A handful of researchers, working late in dim observatories and remote analysis centers, began whispering about a possibility they knew they shouldn't say out loud. The moment came when one scientist quietly entered a single line into an internal memo, a line that balanced dangerously between astrophysics and engineering. Could the event represent controlled material expulsion rather than natural venting? It wasn't an accusation. It wasn't even a theory. It was the acknowledgement of a shape in the dark, a thought that scientists are trained to avoid unless the data leaves no other space to stand. Because the anomaly they were dealing with wasn't dramatic like the blue spectral surge, or eerie like the wow signal alignment. This one carried weight in a different way. It was an absence. A clean, surgical missing piece right where the universe should have screamed. Most comets vent like dying stars, violently, chaotically, shedding dust and gas in long roaring plumes that stretch behind them like torn banners. Every physics textbook agrees on this behavior. Every comet ever observed obeys it. And yet, when astronomers stared at the high-resolution composites of 3I/Atlas, searching for the luminous wake it should have carved across the void, they found nothing. No soft dust glow. No vapor threads. No splintered fragments scattering light. Only a quiet, indifferent darkness. What should have been a bright, glittering scar in space was instead a void, a measurable, quantifiable emptiness that defied both optics and physics. The lack itself became data. Scientists were forced to treat nothingness as if it were a presence. And in a way, it was. The official scientific summaries, careful and controlled as always, reduced the moment to a sterile line. No visible dust tail correlating with recorded acceleration. Possible composition anomaly. But behind those carefully neutral words, everyone knew what this implied. If the tail was missing, the evidence was missing. If the evidence was missing, the mechanism was missing. And if the mechanism was missing, then the event itself had erased the very signs that should have revealed what happened. It was as if 3I/Atlas had performed a dramatic act of mass ejection, and then deliberately covered its own tracks. Some astronomers compared the phenomenon to a ship slicing through a black ocean without leaving a wake. Not because the water was still, but because the ship had commanded it to be still. A comet without a tail is like a voice without sound, a contradiction, an impossibility. Yet the silence 3I/Atlas left behind felt louder than any explosion in the solar system's recent history. It has reminded humanity that the universe is not obliged to follow our expectations, that our models are only approximations, and that sometimes an object appears not to teach us about itself, but to reveal the limits of the frameworks we use to explain reality. In its silence, 3I/Atlas has given voice to a deeper truth. Discovery doesn't begin with answers. It begins with the courage to admit uncertainty. 3I came and went, leaving no answers but an echo, a reminder that the cosmos is not a ledger of certainties, but a treasury of enigmas. In the quiet aftermath, astronomers found themselves grappling not with the object itself, but with the mirror it held up to human understanding. The laws of physics had not failed. Nature had not broken. Rather, the boundaries of our perception, our models, our statistical comfort zones had been stretched, almost to the breaking point. And in that stretching, the universe whispered a subtle but persistent truth: what we think we know is always provisional. To speak of 3I as merely a statistical anomaly is to understate its effect. It was an extreme of extremes, a point on a curve so distant that it bends our conception of what is probable. Individually, each of its peculiarities, the high nickel content, the near absence of water, the anomalous acceleration, the missing tail, the coherent light emission, could be accommodated as rare outliers, unlikely but plausible. But taken together, they formed a constellation of improbabilities that seemed to resist any tidy natural explanation. Each anomaly was a note, and together they composed a symphony that was at once unfamiliar and hauntingly precise. Astronomers began to speak in a new language of probability, one tempered by humility and wonder. It was no longer enough to calculate chance events. The pattern, the coherence, the resonance of anomalies demanded acknowledgement. What might have been dismissed as coincidence in isolation now acquired a gravity. And yet, the emotional undertow was not fear but a peculiar form of awe. For every anomaly presented a challenge to prediction, but also an invitation to imagination. Scientists, trained in meticulous calculation and procedural certainty, found themselves tasting the same thrill that once electrified the pioneers of astronomy: the sudden, unbidden recognition that the universe was stranger than reason, richer than calculation, more inventive than any theory conceived in a laboratory. 3I, in its silent passage, reminded them that knowledge is not a fixed endpoint but a horizon, ever receding, ever luminous. The effect of this realization rippled beyond the immediate community of researchers. Philosophers and writers, cosmologists and students, all found themselves drawn to the tale of an object that defied both expectation and description. In cafes, lecture halls, and online forums, the discussion of 3I took on a rhythm not unlike poetry. It was no longer merely a body in space. It was a narrative, a lesson in the art of cosmic humility. Its existence prompted reflections that transcended statistics. How do we respond when nature presents something beyond analogy? When the improbable accumulates into the impossible, what is the role of human reasoning? The conversation shifted from mechanics to meaning, from equations to experience, and for a moment, the sterile precision of scientific observation intertwined with the quiet wonder of storytelling. One could trace the lineage of such experiences back through history. Consider the first pulsars, whose rhythmic emissions were initially mistaken for signals from little green men. Or the gamma-ray bursts, first assumed to be artificial, later revealed as the dying cries of distant galaxies. These were moments when the familiar scaffolding of expectation gave way to the strange and luminous unknown. And yet, the emotional undertow was not fear but a peculiar form of awe. For every anomaly presented a challenge to prediction, but also an invitation to imagination. Scientists, trained in meticulous calculation and procedural certainty, found themselves tasting the same thrill that once electrified the pioneers of astronomy: the sudden, unbidden recognition that the universe was stranger than reason, richer than calculation, more inventive than any theory conceived in a laboratory. 3 Atlas, in its silent passage, reminded them that knowledge is not a fixed endpoint but a horizon, ever receding, ever luminous. The effect of this realization rippled beyond the immediate community of researchers. Philosophers and writers, cosmologists and students, all found themselves drawn to the tale of an object that defied both expectation and description. In cafes, lecture halls, and online forums, the discussion of 3 Atlas took on a rhythm not unlike poetry. It was no longer merely a body in space. It was a narrative, a lesson in the art of cosmic humility. Its existence prompted reflections that transcended statistics. How do we respond when nature presents something beyond analogy? When the improbable accumulates into the impossible, what is the role of human reasoning? The conversation shifted from mechanics to meaning, from equations to experience, and for a moment, the sterile precision of scientific observation intertwined with the quiet wonder of storytelling. One could trace the lineage of such experiences back through history. Consider the first pulsars, whose rhythmic emissions were initially mistaken for signals from little green men. Or the gamma ray bursts, first assumed to be artificial, later revealed as the dying cries of distant galaxies. These were moments when the familiar scaffolding of expectation gave way to the strange and luminous unknown. This meditation extended into the philosophical domain. What is the boundary between the natural and the designed? Between the improbable and the impossible? 3 Atlas did not provide answers. It merely invited reflection. Some astronomers proposed natural scenarios: formation in a high-temperature star system, retention of heavy metals due to unusual nebular chemistry, or survival aided by a dense metallic crust. Others considered speculative models: controlled mass ejection mimicking propulsion, optical properties suggesting engineered surfaces, or internal energy storage manifesting as coherent light emissions. Each hypothesis required mental flexibility, a willingness to entertain extreme probabilities while remaining grounded in observation. And even the most conservative models carried a tinge of wonder. The universe is capable of producing outcomes so extreme, so finely tuned, that they rival what a mind might imagine in design. Across this landscape of ideas, the emotional current remained striking. Scientists spoke in whispers of poetry and probability, of the tension between reason and awe. There were no grand pronouncements, no declarations of extraterrestrial intelligence, no sensational headlines. Instead, there was a quiet recalibration of expectation, a recognition that observation itself can teach humility. Atlas, in this sense, became a teacher, not of content but of methodology. Its presence asked observers to reconsider how knowledge is built, how patterns are inferred, and how anomalies are understood. In its silence and defiance, it emphasized that the pursuit of understanding is as much an emotional and philosophical journey as it is a technical one. And so, 3 Atlas became an emblem of epistemic patience. It illustrated the need to respect probability, to weigh anomalies without forcing them into pre-existing narratives. It reminded researchers that the absence of a conventional explanation is not a failure, but an invitation. Each spectral measurement, each orbital calculation, each high-resolution composite image became a meditation on scale, chance, and subtlety. The object's passage, though brief on a cosmic timeline, left traces in human thought that would endure far longer. It reshaped how astronomers conceptualize interstellar visitors, how they approach extreme anomalies, and how they balance statistical rigor with imaginative openness. Perhaps the most profound lesson was that of scale. Humanity is accustomed to considering probability and structure on scales we can observe and manipulate. But the universe operates in magnitudes far beyond daily intuition. One object in trillions can embody the extreme tail of a distribution, an outcome of processes that are entirely natural yet appear miraculous from our vantage point. 3 Atlas was such an object, improbable, coherent, and astonishing. To understand it was to acknowledge the vastness of what is possible in a galaxy of hundreds of billions of stars, each with their own complex systems, each conducting a silent experiment in chemistry, gravity, and dynamics. Atlas, in this sense, was both anomaly and teacher, a living proof of the sheer breadth of cosmic possibility. In the quiet of observation rooms, under the dim glow of monitors tracking its final recession from the sun, astronomers reflected on this lesson. The universe does not deliver answers, it presents circumstances. It is not obligated to conform to human logic, and yet in these extreme moments, it invites contemplation. 3 Atlas had arrived without warning, performed a series of phenomena that challenged expectation, and departed, leaving only questions and reflections. In doing so, it redefined the horizon of human understanding, not by revelation, but by prompting inquiry, humility, and awe. The narrative of 3 Atlas thus became a story of adaptation. Scientific teams revised models, simulations, and observational strategies. The passage of 3 Atlas left an indelible mark on the practice of astronomy, not because it could be fully explained, but because it could not. Its journey through the inner solar system, its silent defiance of known physical laws, and the improbable alignment with historical anomalies forced a re-evaluation of both methodology and expectation. Scientists found themselves standing at the threshold between what can be measured and what can only be imagined, a place where observation alone was insufficient, and the act of wondering became itself a form of research. The most immediate consequence was methodological. Instrumentation, once calibrated for the detection of familiar signals and behaviors, was suddenly insufficient for the subtlety and coherence Atlas displayed. Observatories expanded their monitoring protocols to track interstellar visitors across multiple wavelengths simultaneously, with unprecedented temporal resolution. Data pipelines were adjusted not merely to detect motion and mass, but to capture subtle polarization effects, anomalous luminosity, and unanticipated spectral emissions. Every anomaly that Atlas had presented became a benchmark, a test case for what might otherwise have been dismissed as noise. In this sense, the comet's passage was as much a lesson in observational humility as it was a stimulus for technical advancement. SETI researchers, too, found themselves reflecting on Atlas. Its alignment with the coordinates of the historical WOW signal, though never directly causal, demanded renewed attention. Could there exist regions of interstellar space that, by coincidence or design, produce objects whose trajectories intersect with areas of unexplained radioactivity? Could these intersections hint at a larger architecture, natural or otherwise, that we had yet to perceive? The questions were delicate, carefully phrased in academic papers and at conferences, for the line between speculation and sensationalism is perilously thin. Yet perhaps the most striking impact was emotional. Observing 3 Atlas, scientists and enthusiasts alike reported a shared sense of perspective, a quiet humility that accompanies the recognition of scale and probability. Humanity had long measured the cosmos in years, centuries, and eons. We had catalogued planets, moons, and stars, developing elegant theories of formation and motion. But Atlas reminded us that the universe operates on scales and through processes that exceed our imagination, that it can produce outcomes both precise and improbable, subtle yet profound. Its passage was an invitation to wonder, an encouragement to measure not only with instruments, but with attention and reflection. The philosophical implications were subtle but enduring. Atlas challenged the assumption that all phenomena must be immediately comprehensible, or neatly categorized. Its trajectory, composition, and behavior suggested that nature can operate with coherence, purpose, and subtlety that may appear deliberate, yet arise entirely from the uncharted extremes of physics and chemistry. It reframed the conversation, not around whether the object was artificial or natural, but around the human capacity to perceive, interpret, and respond to the unexpected. In doing so, it elevated curiosity above certainty, reflection above assumption, and patience above haste. The scientific community, while cautious, could not help but be inspired. Students of astronomy were taught to see beyond standard deviation and probability curves, to consider the narrative potential of an anomaly. Observational protocols were revised to include more holistic monitoring, integrating optical, spectral, polarimetric, and radio data streams. The analytical frameworks themselves expanded. Probability was contextualized with coherence, statistical independence tempered by alignment, and classical mechanics reconciled with emergent anomalies. The analytical frameworks themselves expanded. Probability was contextualized with coherence, statistical independence tempered by alignment, and classical mechanics reconciled with emergent anomalies. In effect, 3 Atlas became both the subject and the methodology, a living demonstration that the universe teaches most effectively when it remains silent yet unmistakable. For the sleepy professor audience, this offers a meditation not just on astronomy but on approach. The cosmos is vast, unyielding, and profoundly patient. Just as Atlas moved through space with a silent authority, so too must we navigate understanding with patience, humility, and attentiveness. Each new discovery, whether it fits neatly into expectation or defies prediction, is an opportunity to recalibrate perception, expand knowledge, and embrace the beautiful uncertainty that defines the universe. As the final photons of 3 Atlas faded into the darkness of the outer solar system, leaving only the faintest trace detectable by the most sensitive instruments, one lesson became abundantly clear. Knowledge is never absolute. Observation is never final. Probability does not eliminate wonder. And anomalies, those improbable, challenging, and at times inexplicable events, are the instruments through which the cosmos communicates its depth, its subtlety, and its infinite capacity to surprise. For us, for those awake to observe, the passage of Atlas was a reminder. The universe does not speak in loud proclamations, but in whispers, in hints, in the careful, deliberate unfolding of events that challenge comprehension. And it is in those whispers that discovery truly resides. So, as we gaze upward tonight, let us not seek only answers, but questions, subtle, challenging, beautiful questions that demand attention, patience, and courage. For the universe rewards not those who expect certainty, but those who embrace curiosity. And with that thought, we end tonight's journey into the silent, patient, and infinitely surprising cosmos. Remember, in the vastness of space, even silence carries meaning, and every flicker in the darkness is a story waiting to be heard. From all of us at the Sleepy Professor, thank you for looking up with us. Rest well, dream of stars, and keep your curiosity alive. The universe is still whispering.